This is T2, day 29, the ideal soda can sheet. And we're looking at volume of other shapes other than just our boxes from yesterday. So I have a couple of review problems first, and then we'll go to the soda can problem. So the review problem, first one, find the maximum and minimum values just given this equation. So this is out of context, it's just an equation. And we have the interval that R needs to be between 15 and 60. So if we want to find a maximum and minimum, of course, we're going to find the derivative. So we'll take dA dr is equal to 2 pi r plus 2 times that pi. We still have the contents of the parentheses, minus 6 over pi r, and then chain rule, the derivative of this negative 6 over pi r is a negative 6 over pi. Tidy that up some. We've got this 2 pi r, and I've got the 2 pi and also this negative 6 over pi. They're going to need to be distributed into this parentheses. So before I do the distributive, let's multiply the two of these together, and I have a negative 12, the 2 times the 6, and the pi's cancel, and we've got the negative 12 that we'll need to distribute it into this 300 over pi minus 6 over pi r. Using distributive, we've got 2 pi r minus 3600 over pi, and a negative times a negative becomes a positive. 12 times 6 is 72 over pi and r. So our dA dr equals, notice I've got an r here and I've got an r here. So if I factor out the r, I've got the 2 pi plus 72 over pi times r minus 3600 over pi. And the only reason I did that was to observe that this is a linear equation. Y equals mx plus b. I'm going to set that equal to 0. So I have 0 equals this 2 pi plus 72 over pi r minus 3600 over pi. Add 3600 over pi to each side. I've got 2 pi plus 72 over pi r equals 3600 over pi. And then divide each side by everything that's in the parentheses. I've got 3600 over pi divided by this, what's in the parentheses, or I could have multiplied by 1 over the parentheses. So I'd have times 1 over 2 pi plus 72 over pi, which gives me r is equal to, this is ugly, 3600 over 2 pi squared plus 72, which is approximately 39.3. Going to our sign chart, so I'm looking at dA dr. My key value is the 39.3. I'm told that my interval is from 15 to 60. 15 to 60. And again, this is a linear equation with a positive slope, so it would be a line that goes uphill. Negative values, positive values. So downhill, uphill, this is a minimum. And my maximum is going to be either out here at 15 or at 60. So in order to find out what the maximum is, and if I want to know what the minimum value is of A, I know that it is when R is 39.3, but if I want to find out what the A value is, I've got to put all of this into my calculator. So in my y1, I'll type this entire A equation. So y1 equals this. And then go to my table of values, and I'll evaluate A at 15. I'll evaluate A at 39.3, which I know is going to be my minimum. And I'll evaluate A at 60. A at 15, I get 14,744. At 39.3, we get 6164. And at 60, 12,456. So this is my minimum, which I knew from my sign chart. And my maximum is this, because 14,000 is bigger than 12,000. So my maximum. When R is 15, the A value is 14,744. That was a pretty ugly problem. And then another example of those two circles. 100 feet of fencing is used to create two circles. So I'll make a smaller circle and a larger circle. And I have 100 feet of fencing. So I've got circumference, which is 2 pi r. If I let this radius be x and this radius be y, well, let's continue reading the problem. Circle 1 must contain at least 20 pi square feet. So the area of this circle has to be greater than or equal to 20 pi. The area of this circle, area of circle 2 must contain at least 50 pi square feet. So the area is greater than or equal to 50 pi square feet. What is the minimum possible area that can be contained in both circles? So we want to minimize, and also what is the maximum possible area that can be contained in both circles? So we're looking for both of these things. So if I'm looking for minimum area or maximum area, I need an area equation. So my area is going to be the area of the first circle, which is pi x squared, plus the area of the second circle, which is pi y squared. Too many variables, need to get rid of one of them. So I'm going to come over and look at the fact that I have 100 feet of fence. So my 100 feet of fence must be the circumference of the first circle, so 2 pi x, plus the circumference of the second circle, 2 pi y. And if I want to solve for y, I can solve for either of them, but I generally solve for y. I've got 100 minus 2 pi x equals 2 pi y. And dividing each side by 2 pi, I have y equals 100 minus 2 pi x over 2 pi, which I can reduce to y equals 50 over pi minus x. So coming back to my area equation, area equals pi x squared plus pi y, which is 50 over pi minus x squared. So I need to take a derivative, and I have dA dx equals 2 pi x plus 2 pi times the contents of the parentheses raised to the first power, and chain rule, derivative of this negative x is a negative 1. So I've got 2 pi x. Let's bring this negative out front. We've got minus 2 pi and the contents of the parentheses. Distributing that, 2 pi x minus 2 pi times 50 over pi gives me 100. Negative 2 pi times negative x is plus 2 pi x. So dA dx is equal to 4 pi x minus 100. And note again that it's a linear equation. I'm going to set that equal to 0. So I have 0 equals 4 pi x minus 100. 4 pi x equals 100, or x equals 100 over 4 pi, which is approximately 7.96. So we need to go to our sign chart. Key value is a 7.96 linear equation that goes uphill. So I've got negative values, 0, positive values. This is my x. And I'm looking at dA dx. So that must be going downhill, uphill. This is a minimum. Well, I was asked for both the minimum and the maximum. So the minimum I've got my minimum when x equals 7.96. But in order to find the maximum, I've got to come back over here to my constraints, my restrictions. So if I come back to my restrictions, I know that the area of this circle is pi x squared. This is in terms of x, this is in terms of x. So I've got x squared is greater than or equal to 20, or x is greater than or equal to the square root of 20. I don't need to consider the negative because x is a length. So x is greater than 4.5. So then I know that x is greater than 4.5, but I need to find out what is less than. But when I go to this circle, this is pi y squared is greater than or equal to 50 pi, or y squared is greater than or equal to 50, or y is greater than or equal to the square root of 50. But this is in terms of y. I need it in terms of x. So I'm going to use my substitution again from here and have 50 over pi minus x is greater than or equal to square root of 50. So negative x is greater than or equal to square root of 50 minus 50 over pi. Divide by negative 1, x is less than or equal to negative root 50 plus 50 over pi, which is approximately x is less than 8.84. So coming over to here, the minimum that x can be is 4.5. The maximum that it can be is 8.4. So again, over here, I got it in terms of y, this restriction, but I needed to put it in terms of x, so I needed to do a substitution again. So I had an upper boundary for x. And if I'm going to now find out which one is the maximum, I want to know, is this curve higher here or here? So I'm going to come back up to this equation because it's already in terms of just x. If I wanted to use the equation above, I'd need to know both x's and y's. But if I plug this in as my y1 on my calculator, I can evaluate that area at 4.5, the area at 7.96, and also at 8.8. I know that this area at 7.96 is my minimum, and that gave me 397.9 square feet. That's my minimum. At 4.5, 474.3 square feet, and if R is 8.8, I get 402.8 square feet. Well, because this is larger, this is my maximum. So when R is 4.5, my maximum area is 474 square feet. And I would, of course, want to also find out what my y value is. So I would take this 4.5, put it in here, and find the y value. Take the 7.96, put it in here, and find the y value. So I would know how big each of those circles should be. Going down to our new stuff. PepsiCo wants a new can that will hold exactly 355 milliliters of liquid. The can is a cylinder with aluminum sides, top and bottom. Aluminum is expensive, and PepsiCo wants to use the least amount of metal possible to save costs. It is also better for the environment. Find the dimensions of the ideal soda can. Okay, so let's draw our soda can. We've got a circular bottom. We've got the top, the sides, and the top. This would be another good thing for you to make out of paper to see what the construction looks like. So we're told that our volume is 355 milliliters. We also know that the volume of a can is, or any cylinder, is the area of the bottom times the height. So the area of the bottom here, the bottom is a circle, so it's pi r squared, and our height is h. That is, we're letting this equal r, and that's h. So 355 equals pi r squared h. We want to find the dimensions of the ideal soda can that uses the least amount of metal. So we haven't been told what the cost is, so we're just trying to minimize the amount of metal. So the amount of metal, when we think about it, is made up of the sides and the top and the bottom. So we could think about it as being the surface area. If I've got the top and the bottom, I've got pi r squared is the top, pi r squared is the bottom, so I've got 2 pi r squareds. That's the top and the bottom. And then the side, well, if I unwrap this side, if I were to cut along here and open it up, I've got a rectangle. The height of the rectangle is h, and the base of this rectangle has to go around the circle. So the base of the rectangle is the circumference of the circle. So I've got the circumference of the circle, 2 pi r, and then times the height to give me the area of this square. So I've got 2 circles, the top and the bottom, and this rectangle that will wrap around between them. If I want to maximize this, I've got to take a derivative, and again, I've got too many variables. So I'm going to come over here and I'm going to say, well, which one of these variables is the easiest one to solve for? Well, I can solve for h simply by dividing by this. If I wanted to solve for the r, I'd have to divide by the h and the pi and then take the square root. So being a little bit lazy, I'm going to go ahead and solve for the h. So I've just got the 355 divided by the pi r squared. So my surface area is equal to 2 pi r squareds plus 2 pi r times my h, which is 355 over pi r squared. Multiplying that, I've got 2 pi r squareds plus 2 times 355 is 710. The pi's cancel. One of the r's cancels and leaves me with an r in the bottom, but I'm going to bring that up and make it have a exponent of -1 so that I can take the derivative. So my derivative of SA, of the surface area, with respect to the change in r, is going to be 4 pi r minus 710 r to the -2, or dSA over dr is 4 pi r minus 710 over r squared. We'll set that equal to 0 as always. So 0 equals 4 pi r minus 710 over r squared, or 4 pi r equals a positive 710 over r squared. Multiply each side by the r squared, and I have 4 pi r cubed equals 710. R cubed equals 710 over 4 pi. Take the cube root of each side, and I've got r is approximately 3.84, and that's going to be centimeters. My height then is 355 over pi r squared is approximately 7.67 centimeters. I hope that helps. It's the same problem that we've been doing, but again, we need to look at how do we get this equation? What is it that I'm maximizing or minimizing? And that's what I need an equation for. And then we needed to pull apart our can to see how it was made. So again, hope that